Hello everyone. My name is Anup Singh and I'm a PhD student at ID Lab in Ghent University. In this video, I will talk about our paper called Simultaneously Learning Robust Audio Embeddings and Balanced Hash Codes for Query by Example. This is work in collaboration with my advisors Kris and Vipul Arora. Have you ever been listening to a piece of music which could be a new track or a song by unknown band and wondered what it was? In the past, you may have had to ask someone in the hope they knew. But thanks to modern technology, you can now just take an audio snippet and use one of several apps offering music identification services to find more information about the recorded audio. The core technology behind these apps is called audio fingerprinting. Audio fingerprinting allows for generating a compact summary of an audio signal, which is important because it allows for an efficient storage of audio signals and fast retrieval of audios in a large database. There are several key steps involved in building an audio fingerprinting system, including audio segmentation, feature extraction, and audio indexing. There are several applications of audio fingerprinting, such as music identification, which I just discussed right now. Another application is broadcast monitoring, and recent exciting application of it has been in second screen apps, which provides users real-time information on their mobile devices about the broadcast content they are watching on TV. One of the most significant challenges in audio fingerprinting systems is ensuring their robustness against audio distortion, such as noise and reverberation, to accurately identify and match audio signals. Secondly, the system should be efficient, which can expedite the retrieval process and enhance the user experience. Last but not least, the system should be less complex for its practical deployment on a large scale. There exist several methods for audio fingerprinting. However, the conventional approaches rely on handcrafted audio features which are not robust against high distortion levels and lead to inaccurate search results and unreliable performance. Recently, deep learning has been investigated to generate compact audio fingerprints. However, their performance still degrades in high distortion environments, particularly when the audio queries are shorter lengths. In addition, previous approaches do not perform fine-grained audio search, which further compromises their effectiveness. Moreover, indexing performance is also a concern as no prior work addresses this issue. The inefficient indexing can result in significant delay in retrieval process. Therefore, there is a need for a solution that improves all aspects of the system. As a solution, we use contrastive learning framework to generate robust audio embeddings. Then we use transformer encoder that embeds contextual information and generates discriminative audio embeddings. This is particularly useful when we perform fine-grained audio search to precisely locate the query timestamp. To improve audio indexing, we propose to generate balanced hash codes, or to say, we build a balanced hash table. We achieve this by performing balanced clustering using optimal transport framework. As a result, our indexing involves building only a single hash table and less hash bucket pros for retrieval, and thus it makes our audio search more efficient and less complex. Our system consists of multiple stack submodules as shown in the figure on the right. We use contrastive losses to train transformer encodings as well as their projections in a lower dimension space. Now, we propose quantizing these low-dimensional embeddings as a clustering process. So, we treat all possible binary codes of length k as fixed cluster centroids in L2 RK space, and we want the embeddings to be uniformly assigned across these centroids. Furthermore, we want that embedding corresponding to clean audio and its distorted counterpart to be assigned to the same centroid. Therefore, we formulate the clustering objective as follows. Now, note that the neural network may provide us a trivial solution to the previous objective, where all the embeddings are assigned to a single centroid. Therefore, we add a balanced clustering constraint to our objective as follows. However, solving this constraint is difficult to solve since it is a combinatorial optimization problem. So, here we adopt the optimal transport framework to obtain an approximate solution to it. And thus, we redefine our previous objective function as follows. We also propose a simple yet efficient subsequence search strategy which generates multiple sequence candidates to precisely locate the query timestamp. In this figure, we present an overview of our system to build reference database of audio fingerprints as well as for audio retrieval. We evaluate the efficacy of our system in terms of hit rate, and we use an existing deep learning based method as a baseline. Furthermore, we also compare the efficiency of our system in terms of the search speedup that we gain due to the balanced hash codes. We compare our indexing performance with the locality sensitive hashing, also called LSH. In the table, we present the performance of the systems for different query lengths and distortion environments. In the result, we highlight in blue that our embeddings are more robust and thus achieve better hit rate performance given that we have fixed the indexing method, which is LSH. Now, we also highlight in red the search speedup that we achieved while keeping the fixed transformer encoder. The overall performance of our system in terms of effectiveness as well as efficiency is highlighted in green. Note that our system achieves a 10 to 20% better hit rate at high distortion levels, particularly for short query lengths. At the same time, the search speed exceeds two-folds. In summary, we build an audio fingerprinting system which is robust against high noise and reverberation levels. We also propose to obtain balanced hash codes by adopting optimal transport framework. As a result, we improve the performance of our system in terms of efficiency and efficacy. Lastly, we demonstrate that our system performs significantly better compared to the baselines in every distortion environment, particularly with shorter query lengths. Please join us for our poster presentation at the session on music information retrieval, or you can reach out to me by email. Thank you for listening.